Hey guys, welcome back to the channel. So lately I've been working on databases, and you know, with the database you need to, especially for my hard drive, because I was using it on the hard drive. So you want to optimize it for, um, as little I/O operations as possible. So what that essentially means is, each time you go into your hard drive and it's looking for a specific block on the hard drive or whatever, it's one I/O operation for that, and you can imagine that the more I/O operations that you need on average for especially in a database where you have to keep looking up stuff, updating stuff, and all that. Like if you do that a lot, it's gonna decrease longevity at some point. So the way you can kind of reduce the I/O operations needed to do different stuff, like removing things from the database, adding stuff to the database, searching stuff from the databases. You can use something called BPlusTrees. So, I thought I'd make a video on it. So here's the complete code for the BPlusTree, which I'll link in the description below. And to explain the BPlusTrees, I have some resources pulled up here. So I'm just gonna. So here's what BPlusTree looks like, and this is on a BPlusTree visualization website, which I'll link in the description below. But essentially, you notice that there's like a degree with it, which I'll get into more in a second. But here's the tree, right? So I just inserted a whole bunch of stuff earlier, and here's what it looks like for a degree 3 BPlusTree. And what you'll notice is it's balanced, right? So if you look at the leaf nodes, it's all on the same kind of level. So if say this is level 1 and this is level 2 and so on and so forth, all the leaf nodes are at level 3. All the internal nodes here are at level 2, and then the root node here, it's a root node because it doesn't have any parents. It will be at level 1 in this case. So it's completely balanced, meaning you don't have issues with having to go down. Like with some non-balanced trees, you're gonna have issues where maybe I have a root node here, and then it just goes down one branch the entire time. Alright, so for example, with this binary tree, you would have an issue because, say, if you wanted to find 5, you'd have to obviously start at the root, so that's 1. And then you'll see, okay, 5 is greater than 1, we go down here. 5 is greater than 2 here, and then so on and so forth. And it would be very slow, and obviously you'd have to go through 5 I/O operators because if you imagine each one of these nodes as a page, and a page is 4096 bytes, just at least for me, but it's pretty common to be 4096 bytes. So if you imagine each one of these to be pages that you would retrieve from the hard drive to load into memory, right? To update it, to do all kinds of stuff with it, but you'd have to go through the hard drive and find 5 different blocks, and that's just very I/O inefficient in terms of I/O, but it will reduce longevity at some point for sure. So you do not want that to happen. So come back here, you notice that again it's balanced, and if I wanted to find 8, I can just go down. I can just do it in 3 I/O operations, right? So I can just go root node. Okay, that's 1 I/O operation. 8 is greater than 5, so I come down. This child pointer, which I'll get into more in detail in a second here. And then again, 8 is bigger than 7, so I come down this child pointer here and finally find 8. And that again takes 3 I/O operations, which might seem like it's a lot, but the thing is, once this is only a degree 3 tree. Usually, in an actual database, you might have a on average degree 100 or degree 1000 tree. Depending on how many keys you can store in each one of these nodes. And again, from now on, I'll just refer to nodes as pages, because when it comes to BPlusTrees and databases, it's basically just called a page. So you can imagine if we have hundreds or thousands of keys in each page, to search through that with like binary search will take a very short amount of time. So we can easily find which child pointer we have to go down, and that'll be really quick. And then obviously we can go through 1,000 keys in one I/O operation, right? So we can have, we could have a database with hundreds of thousands, even millions of keys, and we can search through that with very minimal I/O operations, right? Especially with a high degree tree that we don't have here, but in an actual database, again, that'll be more common. So, all right, so now let's just go through a few properties of B plus trees. And to preface, B plus trees and B trees are actually pretty different. If you go online and you find something about B trees or B plus trees, you might, especially B plus trees, you might see them used interchangeably, but they're pretty different. So let's get into some of the differences first, actually. So here's the same B plus tree from the website earlier that I just copied onto here. And you'll notice that you'll see the leaf nodes here, which are essentially the very bottom, very bottom of the tree. Right? It's called the leaf nodes. So you notice that they're linked together here in what's called linked list. So you'd have, and this actually isn't fully what you'd have in a like B plus tree. Usually what you have is, if you look at these, right? If you look at these child pointers, they kind of go both ways. So you have a child pointer coming from the parent down, and usually you'd also have a parent pointer from the child node going up, like that. And you'll see why later when we start talking about merging internal nodes and stuff like that for when we're deleting keys, right? And we have to delete from internal nodes. So we'll get into that in a second here. But with leaf nodes, you usually have them in a doubly linked list, right? So this is singly linked list. Sorry, I can't speak. Singly linked list, right? But you want to put it into a doubly linked list. So I'd have 5, pointing to 6 as the 6 would be the next sibling of 5, right? But I'll also store for 5 the previous, right? So, and likewise for 6, we'd store the previous sibling and also the next sibling. Obviously for this node there is no next sibling, so just point to null pointer or whatever. And then same for this one, for its left sibling there's nothing, so it won't point to anything. Okay, so the other main difference outside of that is you notice that every single node, every single key rather, that's stored above the leaf node, so internal or root, it's repeated in the leaf node, and this just the only reason is just so that makes ranged queries a lot easier for especially in databases and stuff. So if I wanted to say, I don't know, give me all the search through keys 3 to 6 or whatever, we'd start off at 3, so we traverse down the tree, get to 3, and then we'll go 3, 4, 5, 6, right? Because it's a linked list, so we can just go through it. And then then we'll have all the keys, and we can do whatever we want with it, right? And the other big difference, actually, there's one more, is data. Okay, so data is stored here only at the leaf nodes. So whatever data is associated with, let's say 2, will be stored here. Whatever data is associated with 7 and 8 will be stored here. So this might be for 7, and then we have some more stuff for 8, right? So it's going to be stored only in the leaf nodes. Everything above it is, so for example, you see this, right? That would just be a child pointer, and all it does is just point to the child, right? And then you see this one, this is another child pointer, these are all child pointers, and this points to the leaf nodes, and the leaf nodes are what finally store the actual data, right? So that's essentially how these work. So going back here and just, let's just talk about the kind of, I guess, rules of a B plus tree. Okay, so here's some properties. So first of all these are at the same height. That's just because the tree is balanced, right? So we've gone through that. And then there are at least 2 children in the root. So, you can have an empty root, or you can, sorry, let me just make this a little thicker. So you can have an empty root if the database is just initialized, right? So if we don't have anything in the database yet, obviously we're not going to have anything to root. And when you first add something into the root, so if we insert something into the root, let's say something with key 3 into the root, at this moment where the B tree's height is 1, because there's only a quote-unquote root, there's actually more than just a root, because this node is actually a root and leaf at the same time. Because if you think about it, obviously it doesn't have any parents, so it's a root, but at the same time it's a leaf, right? Because it's also the very bottom of the tree. That's interesting, especially for B plus trees, because that means this node can also store data, right? Because it's a leaf node. But at the same time, it also needs to store, or it needs to be stored as a root node. At least in the actual B plus tree class, which I'll get to in the code in a second. But just keep that in mind. So, and come back here. Except for the root, each node can have a max of m children and a minimum of n divided by 2 children. So essentially, if we say we have a tree of order m, so if we have a tree of order m, what that essentially means is, and let's say m in this case is 3, right? It's 3. So what that basically means is something like this tree, which I will erase in a second here. Okay, so I'm actually just going to copy this over. And the Linux version of Paint is pretty janky, but it works, I guess. So anyway, you would see you have except for the root, each node can have a maximum of m children and a minimum of, ceiling division m divided by 2 children. So if we look at this, here we have a minimum of, 2 children in this case, because ceiling 3 divided by 2, ceiling division, whatever it's called. We got 2, right? So therefore you have a minimum of 2 children for each of these, but you can have a maximum of 3 children because, again, m equals 3. So for example, in this case you'd have 1, 2, 3. Even this one you have 1, 2, 3 for the root. So right, but the root can have an exception, I guess, when there's nothing in it, right? Like we talked about just now. So that's basically the only case. When it's at both a root and a leaf at the same time, it can have less than this amount of children. And finally, you can have a maximum number of keys being m minus 1. So you can see here we have m minus 1 keys, and if we added any more, so again, when you add nodes to when you add keys to a B tree, you always add it from the bottom here, right, from the leaf node. So in this case, if we added 9, it'll obviously it'll go right here next to the 8, and then you'll see that this node will contain m children once we add, m keys once we add another key in here. And when that happens, you have to split the node, which I'll talk about in a second here when we get to inserting and deleting stuff from trees. Right? So, and then you can also have a minimum of, in this case, that'll be 1, right? Because ceiling division 3 divided by 2 equals 2, minus 1 equals 1, and in this case, you can see right here that is 1 key in there. Can be stored in each node. So if we drop below this, threshold of 1 key, so for example, if we're doing deletion in this tree and I delete it 2, it'll drop below the minimum number of keys that we can have, and in that case we'll have to start either borrowing from siblings or merging with siblings, which again we'll get to in a second when we start talking about the removal from B plus trees. Okay, so now we're going to talk about inserting, and inserting is probably the simplest operation in there's only really inserting and removal of keys from that for now, so it's pretty simple. And let's say we have an empty thing going on here, right? And we insert 1, so we're gonna put 1 here. And obviously, every time we insert something to a B plus tree, it comes with a value. But I'm just gonna omit the value for now. But just remember that there is a value associated with all the leaf nodes. And in this case, again, this node is both a leaf and a root at the same time because, the B plus tree only has a height of 1 right now. Okay, so now let's say we, again, I'm just going to say this is a B plus tree with order 3. I'm actually just going to write that down first. Order 3, right? So now let's insert 2. And, we can insert 2 right here. Reason being that, and again, this is on the same node. Reason being that our node can have a maximum of 3 minus 1 keys, right? And this is fine because, now we're at the maximum number. And you'll see that, let's say we insert 3 now. We'll reach 3, and obviously you can't do this because now this node will have 3 keys, which is equal to this, and that's going to exceed the 3 minus 1 limit, right? So what we do now is we divide we divide this by essentially n divided by 2, but we want it to be floor division. So in this case, that would just be 1, right? Because 3 divided by 2 floor is 1, right? So we slice it off at index 1 in this node. So we leave this node at index 0 in the node, or we leave this key at index 0 in the node behind, and we take everything after that, so in this case index 1 and index 2 over, and we'll split it up. So now what we have is we'll have this. So this is by itself now, right? So this was index 0, and then we're going to split it off, and obviously doubly linked list. We're going to split it off 2 and 3. Right, so the 2 here was the previous key at index 1 in this node. So what's going to happen is, obviously now we're going to need a new root node, right? Because we split it up, like, we need a new root node. So what we're going to do is we're going to upgrade 2 into a root node, or into the new root node, yeah. So here's 2, right? And then obviously here's the parent, here's the child pointer, same thing here. And now you have this. So now 2 is going to be the root node, and 2 doesn't have a value associated with it anymore because it's no longer the leaf node, and then the values are still here with the leaf nodes, right? So you still have this. And basically what we just did here was, once we split it off, again, to reiterate, we took the key at the index that we split at, so we split at index 1 right here. So the key at index 1 moves up and it becomes the new root, just like that. Alright, so let's keep going. So let's say I added, and actually I'm just going to make this a little less messy by removing these pointers that we don't need here. Well, I mean, we need them, but just to make it a little simpler. So now let's say we added 4 in here. So we added 4. Now again, you're going to notice that this node is going to exceed that limit, right? Because we can only have n minus 1 number of keys in this node. So I will, again, slice it at this index 1 line here. This 2 is going to stay by itself. 3 and 4 is going to move over. And 3 is also going to move up into the internal node. Or, yeah, it's going to move up. And we'll make this happen here. So I'm just going to erase all this. So 2 is going to be here. Again, we're going to have the left and right pointers. Actually, I'm going to draw this one as well. This one points to nothing, obviously, because there's nothing to the left of 1. And then 3 and 4 gets moved over. Just like that. There we go. And then 3 is going to get kind of quote-unquote upgraded into the position up here. So now we're going to have an issue here because we can't just do this. Reason being that each kind of node in the B plus tree can only have a maximum of 1 parent. So in this case, we're gonna have 2 is gonna have 2 parents, and we can't do that. So what's going to happen is we're going to join it together. It's like this. 3 and 2 is going to join together because, and just like that. So we're going to join that together. Reason being that the node, with just 2 earlier just now, that's obviously below the maximum threshold of n-1, which is equal to 2. So now we're at the maximum, but it's still fine now. So once we add a 5, we'll see what happens once the internal nodes reaches the maximum. So let's say we add a 5 now. So we add a 5. So what's going to happen? Same as before. It's going to exceed two keys, right? So we're going to slice it again right here. And we're going to have 3 stay behind and 4 and 5 move over. So I'm just going to move that over like this. So again, pointers and 4 and 5. Obviously this node always points to nothing because there's no node to the right of it. And again, 4 will move up. So 4. Because 4 was at the index 1 in this node earlier that we split up. So it moves up just like that. Now, the issue here is I guess this will be the root node. The root node exceeds the maximum threshold of keys we can have. So what we do here is we do the same thing as before. We want to split right here. So we're going to split it here because, split index 1, reason being that 3 floor division 2 is equal to 1, so split index 1, right, so let's split that off. So I'm just going to do that like this. Sorry, it's a little clunky. Essentially we're going to have 3 and 4 off to the side. Now the difference between internal nodes and leaf nodes is when we split off an internal node, when we split off, for example, this 4 and 5 earlier, we kept this 4 in this leaf node because the leaf node needs to contain every single key that's in the database, right? Or that's above it, right? So in this case, 2 is in this internal node, so we have 2 here. 3 was in this internal node earlier, so we have 3 here. So on and so forth, right? But with internal nodes, we don't need this, so we don't need to repeat. So what we're going to do is we're actually going to still upgrade 3 up, but we're going to also not bring 3 over. So it's actually going to look something like this. So 3 actually becomes the new root node of the entire tree. And then we keep this child pointer and this child pointer. Now one thing you might realize now is when it comes to the this layer right here, when it comes to this layer, you'll notice that it's 1 layer above the leaf nodes, and the key in here, right? So this is at position 0. It corresponds with the key at the child pointer 1 at position 0 in that node. So here's child. Okay, so let's say this is child pointer 0. This is child pointer 1. This is going to be the same as the first key in the node that's pointed to by child pointer 1. That kind of makes sense. So for example, with 2 here, 2 is going to be equal to the to this node, right? Or to this key, sorry, which is the first key in this node that is pointed to by this child pointer, and this child pointer is child pointer 1, which is basically this key, which is at index 0 in this node plus 1. Same thing here. This key is at index 0, right? And then the child pointer is just key plus 1. So in this case, 1, right? And then I hope that makes sense. But it's not really that important. It's just a thing that you can utilize when you're actually writing the code out for the BPlusTree. So I'm just gonna undo. Okay, so now we have this, and this will be the new root node, and and From here, it's the same thing if we keep inserting. Eventually, if let's say we insert 6, right, we're going to split that off. And then 5 is obviously going to move up, like that. And then it's, these start split up now. So these start split up. If we add a 7 maybe, add a 7. Now this is going to be split up, right? And then it's going to be split up. And then 6 is going to move up. And then, this will have to be split up. And then only 5, which is the index at which we split up, right? So split out index 1, so 5 is at index 1 in this in the keys here, assuming 4 is index 0. 5 moves up, and then 5 goes here. And then, we split it up, and then 6 will now point to these two, right? So, and so on and so forth. It's basically the same thing all the way up for inserts. So now let's get into deletes. And deletes is probably the most complicated just because it has a bunch of different cases. So let's talk about that. Okay, so let's first talk about, for deletions, the leaf nodes. So deletion from the leaf nodes is probably the easiest just because it's pretty self-explanatory. So if we delete 7 from this node, obviously we'd be fine because this node still contains the minimum number of keys that we need, right, for it to still abide by the B+Tree rules. So in this case, if we delete 7, we still have 1 key left in here, which is fine. Right? Now, if we deleted the 8 as well, now we drop below the minimum threshold, and then we'll start having to talk about cases. So let's say we have this right now, and we just deleted. We'll go back here actually. Let's start with something easier. So let's say we just deleted. Let's see. Let's say we delete 4, for example, right? So delete 4 from this leaf node, and when it comes to deletion, it's kind of the same concept with insertions and deletions, where you start from the leaf node and you work your way up recursively. So to search for the node to delete in the first place, we'll just search through the B tree, and it's pretty easy. So we start from the root node as always. Start from the root node as always. And then in this case, if we're looking for 4, 4 is in between 3 and 5. So we go down this chalk pointer, and we get to 4, and 4 is obviously lesser. 4 is more or equals to 4. So we go down, right, the chalk pointer to the right, and then we finally get to that 4 there just now, and then we deleted that 4, right? So that's essentially how we do it. Once we deleted this 4, we want to kind of close ourselves into this little box here. Just like right here. So reason being that we don't want to look at this 5 because this 5 has a different parent than this 4. So we don't even worry about it. This 3 is the only other node that is immediately to the right or left off the leaf node that we just deleted from that shares the same parent, being this 4 in this case. Okay, so once we've enclosed ourselves in this little box, we can ask ourselves 2 questions. First of all, is this node that is right next to the node that we just deleted from, is it below, like if we took from this node, right? So if we theoretically took away from this node, will it be under full, or in other words, will it drop below the minimum threshold? And so, if it does drop below the minimum threshold, we'll need to merge, right? So we'll need to merge these 2 nodes together. Now, if it does not drop below the minimum threshold, so if in theory we had this was like 2.5 and 3 in here, right? We took away one of these, we would still have 1 left, and that means it's at the minimum threshold, and we're fine. So what we can do in that case is just borrow from here. So in this case, obviously, if we took away this 3, right? If we took away this 3, this node would drop below the minimum threshold, and we can't afford to do that, or we'll break the B+Tree rules. So what we'll do is we'll merge, and essentially how we merge is we always so if we have two nodes, right? If we have two nodes like this, we always merge into the node on the left side. Or at least that's the way I did it for my code, just because it's a little easier. I guess you could also do it for the right, but you have to be consistent with it, right? So you always merge into the right side. But in this case, I'll just merge into the left side. So obviously there's nothing in here, so when we merge, we just put nothing. We put everything, all the contents in here into this node. But obviously, since there's nothing in here, there's not much to move over. So, and once we move it over, we just move over nothing because there's nothing in here. We'll just delete this this node. All right, so we delete this node, and we also delete this child pointer, I guess, because why not, right? All right, so now we're done with this, and we're gonna essentially move up into the parent. All right, so we got done with the leaf node, and now we're recursively looking into the parent. So now we're here, right? Now we're here, and we're gonna once again delete from here, right? We're gonna delete. Now, what's gonna happen is once we delete, the internal node is also gonna be under full, right? Because it's gonna have less than one child. In this case, it's empty. So we have okay. So again, we're gonna look at this box here. It's kind of little box here. Reason being that this node is to the immediate left of the node that we just deleted from. This node is to the immediate right of the node we deleted from, and both of these share the same parent, right? And I like always look into the right child first, or right sibling first, rather than the left. You can look to the left as well, but it doesn't really make a big difference. But we're gonna look to the right at this point. So you're gonna notice that in this right sibling, we have more. If we took away 6, for example, we're still gonna have more than the minimum threshold, which is 1. So we're safe, right? We can take away the 6. So now, over here we merged, right? Down here we merged because this 3, if we took away the 3, would be under full. Now in this case, we can take away the 6 and be fine. So we'll borrow in this case. And the way we borrow in internal nodes is we borrow through the parent. So if you think about it, if we had, in this case we have 4 here, right? Or I guess we have nothing here because we deleted it. So we have nothing here. Here's 5. I don't care what's here. Here's 6. Whatever. Doesn't really matter what goes on here. But how we delete this is it's kind of like a counterclockwise kind of cycle here. So 5 moves down, and then 6 moves up and takes the place of this key in the parent node, and then 6, since 6 gets moved up, whatever was in here. So this internal node, like its key size, it's the number of keys in this node obviously minus 1 because one of its keys moved up, right? So if we apply this, what it's going to look like is we're going to take this 5, we're going to move it down, so we're going to have 5 here. Alright, and then we're going to take this 6, and we're going to move it up here to the parent. And then finally the 6, since we moved it up, it's just gone from here. So now what we're left with is or at least what we're left with in the sibling node is just a 7. And again, the number of child pointers in this node is going to be 1 more. It's always 1 more than the number of keys we have. So in this case, because we have 1 key, we have 2 child pointers, right? And then now we have this, and we still have this pointer down here, and we have this pointer here, and obviously we still have this leaf pointer, and that completes our deletion. So you'll notice that once again, if we take a closer look at this 5, it's 5 because this is at index 0 in terms of the key, and since it's 1 above the level of this leaf, like the leaf nodes, it's the same as the first key in the node that's pointed to by the first child pointer, and it's the first child pointer that we're looking at because again the index of this is 0, right? So 0 plus 1 equals 1. So we look down the first child pointer, the 0th child pointer again, this is the first child pointer. We look down the first child pointer. We get the first first key, and it matches up, so we're good. And so therefore it completes a deletion. So let's try something else. Let's try another number to delete. Okay, so now we're back here, and let's say this time we want to delete something different. Right? One different case. So let's delete, let's say 6. Right? So again, we're gonna traverse down the tree, blah blah. 6 is more than 5, so come down the pointer to the right, the child pointer to the right of the 5. And then 6 is more or equal to 6, so we go down the pointer that is to the right of 6, and we finally get to 6, and then we delete 6. Now, same as before, we want to look to the immediate left and right sibling, right? And you'll notice that in this case, we can look at both of these because both of these share the same parent as the node that we just deleted from. But first, we're going to give priority to the right node right here, right to the right node, just because that's the way I implemented it. But obviously, it doesn't make a big difference. So we're going to do that. We're going to look in here now. Again, we're going to do some analysis, right? If we take away one of the nodes, one of the keys in here, sorry, when we take away one of the keys in here, it's not going to be under full this time, right? Because we still have one node in here. We still have one node being 8 in here. And the minimum number of nodes that we need for it to not be under full is 1, right? So we're good. Okay, so what we're going to do is essentially borrow from the leaf node. And for leaf nodes, when we're borrowing, the difference between borrowing in the leaf node and borrowing from the internal node is we don't do it through the internal, or we don't do it through the parent node, we just do it directly. So we're just going to grab that 7, and we're just going to move it here. Okay, cool. So now that we've moved the 7 here, we're going to go up, right, recursively into the parent node. And now in the parent node, we're going to delete this and change that to 7. And the reason we changed this to 7 is because, again, because it's one layer above the leaf node, and 7, well, this was 6, and this 6 was at the 0th index in this key, so therefore 0 plus 1 equals to 1, and we look down the first child pointer, right, first child pointer in here, this is the 0th child pointer, this is first child pointer, this is second child pointer, we look down the first child pointer, and then we go, use this new key at the 0th key index in the first child pointer, and that's 7. So we have to do the 7. All right. So now we're gonna, once we updated this to be 7, we're gonna look to the key next, or to the right of the 7, because we borrowed from the right side, right? Borrowed from the right side, so we're gonna look to the right key. And we're just going to update the 7 to be whatever was over here. Well, or not whatever was over here, but the new kind of first key in this node, which is 8, right? If we have more, like 9 or whatever, it doesn't really matter. Because it's the first key in this node, right? It's the first key in this node. So we update it to that. So now it becomes 8. So now we have completed deletion of 6, right? So again, we can verify that this is correct because 7, right? This is the first layer above the leaf nodes, and 7 is at index 0 in the keys here, and this is child pointer 0, this is child pointer 1, this is child pointer 2, and you can see 7 corresponds with the first key in the node that's pointed to by the first child pointer. And if we look at 8, right, 8 is at index 1 in the keys, and if we look at 1 plus 1, which is 2, we go down to child pointer number 2. The first key in this node pointed to by child pointer number 2 is 8, so that works out. So that completes the removal. And so let's try one more. So so far what we've gone through is for leaf nodes. We've went through borrowing, right, and also borrowing, like in this case deleting 6. And also we've went through merging, right? So we deleted, 4, I think, right? We deleted 4, we merged, right? We merged with 3. So we've went through merging deletion for leaf nodes. And we've went through, I believe, went through borrowing for the internal nodes. So now let's try merging for the internal nodes. Okay, so now let's find a case where we'll have to merge the internal nodes, right? And one way we can do that is by deleting 2. So let's follow this chain down. So 2 is less or equal. 2 is less than 3, strictly less than 3. So we go on the left child pointer to 3. Okay, and then now we are at 2, and then 2 is obviously more or equal to 2. So we go on this child pointer to the right of 2, and we finally end up at this leaf node, and that is correct. So that is indeed 2, and we'll delete 2 from here. Now once we delete this 2, this node will be under full, right? So this node will be under full. And we looked only to the immediate left in this case because the node to the immediate right of this node doesn't share the same parent, so we don't care about that one. So we're just going to look at these 2 nodes. Okay, now we're going to notice that this node containing this 1 here is going to be under full if we remove this 1. Right? If we remove this 1, there's going to be nothing here. It's going to be under full. Right? So what we're going to have to do is we're going to have to merge. And again, as always, when we merge into the so if we have this pair here, we'll merge into the left node. Right? We'll merge in the left node. So we can do that, and obviously, I mean, there's nothing to merge in here because it's empty. So just pretend, we moved it over. Nothing's going to be added, obviously, because there's nothing in here. So we can just delete that node once we're done with the merging, and we can complete. We do have to update this this kind of doubly linked list, right? If we have to delete this node here, whatever this node that we just deleted was pointing to, we have to give it to this one, and so on and so forth. Just make sure we get the doubly linked list fixed, right? So once we're here, we're gonna move up into the parent, which is 2. Right? Same thing. So we're gonna delete 2 because we're trying to delete 2. And then once we delete this 2, again you'll notice that it becomes under full. And when it becomes under full, we look to the immediate right first and the immediate left. In this case, there's nothing to the immediate left, so we only look to the immediate right. And you'll notice that also the immediate right shares the same parent, so we're good. And now we're gonna merge because earlier when we deleted 4, we could take away this 6 from here without this node being under full. But if we take away 4 now from this node, then this node is going to become under full, right? And we can't afford that. Or it's going to violate the BPlusTree rules. So once again, we're just going to merge. And the way we merge is same as the leaf nodes, right? We always merge into the node on the left in the pair. In this case, it's this node, right? Because this node will be on the right in this pair. And we also want to do it through the through the parent node. So we want to first move this over first, right? This this child pointer is child pointer 0. This child pointer is child pointer 1. This child pointer is child pointer 2. Right? And because this node over here that we just deleted from corresponds with child pointer 0, we delete the 0th index in this parent node, and we move it over, right? So we delete 3, so delete 3, and we're going to move 3 over. Now, once we move 3 over, once we move the node in the parent, or once we move the key in the parent node over, we can begin to copy over the contents of the node here. So obviously, there's only one node to copy in here, so I'm actually just gonna kind of move it over. And again, let's see how we're going to do this. So I'm just going to copy this, and we're going to move it over. Right. Sorry, just going to make this look a little nicer. Ah, there we go. So we've copied this key over, right? And now we're done. So once we're done, we clean up. So obviously this child pointer is going to disappear because there's no longer a key here. And this parent node is only going to contain 5. It's only going to contain 5. And this little point here, right, that's a parent still of this new combined node. And this still exists, right? This pointer still exists. Now we're going to have this pointer pointing here. And finally, we're going to have this pointer pointing to 4 right here. And this completes our deletion. And we can verify this again by looking at this. So 5, this is correct. This 3 is this 3 is strictly less than 5, whereas this 6 is strictly greater than 5. And now we're looking down here. Obviously, 1 is strictly less than 3, and then the 3 here, since this node is 1 level above the leaf nodes, and then this key here is at position 0 in the keys of this node. We go 0 plus 1 equals to 1, so we look down the first, again, this is the 0 child pointer, first child pointer, second child pointer. We look down the first child pointer, okay, we go to this node, look at the first key in this node as a 3, and this is a 3, so that's correct. And then, same thing here, so this is a 4. 4 is the first index in this key, or first index in the keys of this node. Right, so we're going to go down 1 plus 1 equals to 2. So we're going to look down the second child pointer, go to 4, or go to this node containing 4, and we'll notice that 4 is the first key in this node, and it matches up with this, so that's correct. And we complete the removal. And at this point, you'll notice that we've went through borrowing and merging in the leaf nodes, and also borrowing and merging in the internal nodes. And the biggest thing with removing, especially implementing the removal from BPlusTrees, is just the whole pointer thing. So make sure you're really keeping track of this whole pointer updating. For example, here, or when we were merging over, we also brought over the pointers that were associated with 4 just now, and just all that kind of stuff. And when we inserted, well, I don't have it here anymore, but when we inserted, we when we have a new root node, you have to make sure to update that new root node as the root, as the new root node of the B tree. So I'm actually going to pull up my implementation here, which again, I'll link the GitHub repository for that code in the description below, so feel free to check that out. Okay, so I'm back in VS Code here with my implementation, and if we actually look up here to set, right? Set. So this is when you're setting a new node. This is the function I wrote for it, and you'll see right here it says, if we have a new root node from splitting our node, right? Because we're inserting, and then if the insert causes that node to be bigger than the maximum threshold, we split the node, and then we have a new root node. So if we do in fact have a new root node, I'll update the root node of the current B tree to that new root node, right? So that's that. And yeah, so right here is the removal, and you can see I have a bunch of functions for borrowing and merging with the internal nodes, and borrowing and merging with leaf nodes. And here's how you can test it out. So if we I have the set functions for updating and inserting, and the remove functions for removing, and print tree for printing out the tree and visualizing it. Right. So if we go back to the BPlusTree we were looking at earlier, this one in particular, I can verify that inserting is, so this set 2. I can verify that inserting is correct by inserting 1, 2, 3, 4, 5, 6, 7, 8, and it should look like this tree. So let's get to that real quick. Alright, so we're going to run it here. I'm going to compile it first. Okay, I'm going to run it. And you can see this is the, oh, sorry. I know that's wrong. Okay, so here's how I set the order of the B plus tree, right? So obviously in this example here we had an order of 3, so I'm gonna set this order to be 3. I'm gonna recompile, and you can see this is what we end up with. So this is the root node. This is the 3 children of the root node, and then finally these are all the leaf nodes, right? So we can verify this. So actually, I'm just gonna, kind of copy this over here and resize. You can see it's pretty janky, but it works. Okay, so again, this you'll see this matches up, and yeah. So if you want to further analyze or perhaps fork this implementation of the BPlusTree in my GitHub, go ahead. Alright, so that's about it for the BPlusTree tutorial, and if you guys enjoyed the video, make sure to hit that like button. I'll probably be making some updates on the actual database project after this, so if you want to stay tuned for that, make sure to hit that subscribe button. And I don't know, have you bought this video? I don't know. Alright, see you guys. Have a good one.